Alright, welcome back everybody. I hope you had a wonderful 4th of July weekend. Just a little disclaimer, I told you I was sick last week, and with any sort of sickness comes a cough that has my whole life, and it is the reason why I sound the way that I do right now, and most likely will sound this way for the next few weeks. A little benefit about this asynchronous class is that I can edit out any coughing fit so that it doesn't take up class time. So that's a little fun tidbit. Anyways, let's jump into section 3.2, which is exponential and logarithmic functions. So last section we actually learned how to calculate our first derivative, and so in this section we're just adding a few more rules and we're going to go ahead and calculate some more derivatives. Alright, so the first rule is the exponential rule. So if we have the derivative with respect to x of some exponential function a raised to the x, alright, where a is some constant, alright, just any number. So the derivative of a to the x is going to be the natural log of a times a to the x again. Okay? And we have a few special cases of this. First one is the derivative of e to the x. Okay? This is just e to the x. So e to the x, the function, is its own derivative. And if you took the derivative again, so the second derivative, it's going to be the same thing. You're just going to keep getting e to the x. Okay? And another case we have is if there's a coefficient in that exponent. So if we have e to some coefficient k times x, we are going to end up with, we bring down the coefficient, so k e to the kx. Alright, so again, where k is a constant. Okay? I'll just make a quick little note over here. If we had e squared, does this fit into any of these rules here? And the answer is it does not, because this is itself a constant. Alright, so if we were to take the derivative of e squared, so the derivative with respect to x of e squared is 0, because we know that the derivative of a constant is 0. Okay, other than that, we have these 3 exponential rules. And then we have the derivative of a natural log. So the derivative with respect to x of the natural log of x, well, this is going to be 1 over x. Alright? And those are the 2 rules for today. So we're going to go ahead and jump into example 1, where we just need to calculate some derivatives using these new rules. So for part A, we have f of x is equal to 2 times 3 to the x plus 5e to the x. Alright, so f prime of x is the derivative of everything we see over here, so 2 times 3 to the x plus 5 times e to the x. Okay, here we use this little dot symbol just to really separate and see that the exponent of x is only applied to 3. We could also use parentheses. Alright, so basically we're just trying to show you that the x does not also apply to 2. Alright, so we have this here. So the first thing, if we remember from 3.1, is that our derivatives can be split over a sum. So we'll break this into 2 derivatives of 2 times 3 to the x plus the derivative of 5e to the x. Alright, The next thing we learned is our constant multiple rule, where we can go ahead and pull constants in and out of derivatives. So we'll pull the 2 out of our first derivative and then pull the 5 out of our second derivative. Okay, so here we need to use 2 different exponential rules. Okay? So we're going to leave this 2 outside here, and we'll put our work inside of brackets. So the derivative of 3 to the x, well, we remember the derivative of a to the x is natural log of a times a to the x. In this case, a is 3. So we'll have the natural log of 3 times a to the x, but a is 3, so 3 to the x. Okay? Then we have plus our 5 times our next derivative. So we have the derivative of e to the x, which was one of our special cases where it's its own derivative. So the derivative of e to the x is just e to the x. Alright, so here we finished calculating the derivatives, but now we can clean it up a bit more. Okay, so we'll go ahead and say this is 2 natural log of 3 times 3 to the x plus 5e to the x, and this is our final derivative. Alright, we'll go ahead and move on to part B. So we have f of x is equal to 2 natural log of x minus 7e to the negative 0.2x. Alright, so again, a lot going on here. Let's go ahead and see how we can break this down. So f prime of x is the derivative of everything over on the right-hand side. Okay, we could go ahead and break this into 2 different derivatives. So we have the derivative of 2 times the natural log of x minus the derivative of 7e to the negative 0.2x. Okay. For our first derivative, we can go ahead and use our constant multiple rule again, where we pull the 2 out front. So we have 2 times the derivative of the natural log of x. And we'll do that again over here. So we'll go ahead and pull the 7 out. So we have 7 times the derivative of, with respect to x, of e raised to the negative 0.2x. Okay. So then we have 2 times the derivative of the natural log of x, which we just learned is 1 over x. Okay. So then we have 7 times the derivative of e to the negative 0.2x. Alright, so this is one of our derivatives of e to the kx, right? Where we have k is equal to negative 0.2. So the derivative of e to the kx is k e to the kx. This is one of our special cases. Alright, so if k is negative 0.2, we're going to have negative 0.2 times e to the negative 0.2x. And that is our derivative of e to the negative 0.2x. Alright, so finally we can go ahead and drop all these brackets. So we have 2 over x. We have minus 7 times a negative 0.2, which is going to become a positive 1.4 e raised to the negative 0.2 x. So this is our final answer. Alright, so example C, we have f of x is equal to 15 e raised to the 1/3 x minus 17x. So f prime of x is equal to this whole derivative of 15e to the 1/3 x minus 17x. We'll go ahead and break this into two separate derivatives. So we have the derivative of 15e to the 1/3 x minus the derivative of 17x. So then we need to go through and use our constant multiple rule again, where we pull the 15 out front. So we have 15 times the derivative with respect to x of e to the 1/3 x. And again, we'll pull the 17 out over here, so we just have the derivative of x with respect to x. So now we need to go through and go ahead and calculate each one of these derivatives. So we have 15 times the derivative of e to the 1/3 x. This is again one of our e to the kx problems. So k is 1/3. We need to bring that out front. So we need 1/3 e to the 1/3 x. We don't touch anything in the exponent. We don't subtract anything for our exponential functions, okay? Close that bracket off. And then the derivative of x with respect to x is just 1, right? I've seen that a few times already. So we could go ahead and clean this up, and we end up with 5 e to the 1/3 x minus 17. Alright, we have one more, just a calculation of a derivative, and then we'll jump into something else. Okay? So here they switched up the variable on us. Now we're looking at f of t, but it's the same deal, right? So we have f of t is equal to 4 e to the 3rd power, so e cubed, plus 2.45 times the natural log of t. Alright, so we need f prime of t, and that's going to be the derivative with respect to t, so d over dt, of everything on the right-hand side. So we have 4 e cubed plus 2.45 natural log of t. So we'll go ahead and break this into two derivatives. So we have the derivative with respect to t of 4e cubed plus the derivative with respect to t of 2.45 natural log of t. Alright, so we might start right in with the constant multiple rule. Okay, but what do we notice about our first term? We're taking the derivative with respect to t of 4e cubed, which has nothing to do with t, does it? There is no t involved. No t here. Okay, so that should tell us there's no variables, which means it must be a constant. Okay, so 4e cubed is a constant. And we know that the derivative of a constant is 0, isn't it? So we could just go ahead and say, well, that's 0 plus whatever this derivative is. 2.45 natural log of t. Okay, so let's find out what that derivative is. Now we can use the constant multiple rule. Okay, we can go ahead and pull that 2.45 out of there times our derivative of the natural log of t. So if our derivative of the natural log of x is 1 over x, then the derivative with respect to t of the natural log of t, well, that is just going to be 1 over t. Go ahead and drop these brackets. We'll end up with 2.45 divided by t, and this is our final answer. Alright, so I said we were done just blindly calculating derivatives, so now we have one with a purpose. Let's go ahead and find the equation of the tangent line to this function. G of x is equal to 2 times e to the x plus 3 at x is equal to 0. Okay? So we did an example like this last time. Now we're going to follow the same steps, just using our new rules. Okay, so the first thing we need to do is we need to get the slope of the tangent line. Get the slope of the tangent line. And to do this, we must calculate the derivative. At x is equal to 0, right? We need to calculate the derivative and then we need to evaluate it at the point, right? So let's go ahead and calculate g prime of x. So that's going to be the derivative with respect to x of 2e to the x plus 3. So this is the derivative with respect to x of 2e to the x plus the derivative of 3, which is a constant, right? Plus 0. I went ahead and skipped a little step there. Hope everyone's alright with that. Constant multiple rule says we can pull this 2 out front. Then we just have the derivative of e to the x, which we know is itself, right? So the derivative of e to the x is just e to the x. So we end up with 2e to the x. That is our derivative. Okay? So we calculated the derivative, but this doesn't give us a slope yet. We need the slope at a point. So we need g prime of 0. So evaluate at x is equal to 0. So g prime of 0 is 2e to the 0. And anything raised to the power of 0 gives you 1, right? So this is really just 2 times 1, so we get 2. So our slope, which we normally use the letter m for, is 2. And remember the last time we were looking to find a tangent line equation, we looked at the slope-intercept form, and we also looked at the point-slope form. And we ended up using the point-slope form. However, we were missing a piece that we had to find. So we have a slope, and we have half of the point, right? We have the x value, but we need to find the y value. To use point-slope form of a line. And we find the y value by evaluating the original function at the x value. So y is equal to, I'll say y when x is 0, little quantifier there, is equal to g of 0. So this is our original function, not our derivative. Our original function, which was 2 e to the x plus 3. So here we have 2 e to the 0 plus 3. We just talked about how anything raised to the 0 is 1, so we have 2 times 1, which is 2, plus 3, we end up with 5. So we have our slope is equal to 2. We have our x and y values of 0 and 5. So now we need to plug them into our point-slope form, which looks like this, where our point gives us our x1 and y1 values. So we have y minus 5 is equal to 2 times x minus 0. Okay, so y minus 5, oops, that's a wild looking 5, 5 is equal to 2x. We don't need to, or 2 times 0 is just 0, right? So we'll leave that alone. We'll go ahead and move the 5 over to the other side. So we get y is equal to 2x plus 5, and this is our equation of the tangent line. Tangent line at x is equal to 0. Okay? Next we'll look at example 3. Suppose $2,000 is deposited into a savings account that earns 8% compounded continuously. Find an equation for the balance f of t after t years. Find and interpret f of 20 and f prime of 20. Okay, so let's remember that we have two different ways to express an exponential function, right? Two ways to write exponentials. So we have the general way, which is p is equal to p naught a t, and then we have the continuous way, and that is p is equal to p naught e to the k t. Sometimes k is written r instead of k. So we have to think about which one are we using here. Well, they give us a nice clue. We have compounded continuously. So that means we want to use our continuous exponential function. All right, so P naught needs to be the starting amount of money. So P naught is our starting amount of money, which is $2,000. All right, then we have E, which is just E, to the kt. So t is going to be years, right? And k is our rate. So we know that the savings account is earning interest at 8%. Okay, so our rate is 8%, but in decimal form, which is 0.08. All right. So we have our function f of t is going to be 2,000, which is our p naught, our starting amount of money, times e raised to the k, 0.08, times t. So we found the equation. All right, and that's going to represent the balance after t years. So the next thing we need to do is find and interpret f of 20 and f prime of 20. So f prime of 20 is pretty simple. We just need to go, or f of 20, we just need to go ahead and plug in 20 to our equation, right? So we get 2,000 e to the 0.08 times 20. All right, I'm going to put parentheses up here so we know that all of that is in our exponent. And I'm using a little cross instead of a dot just because of that decimal there. I don't want to get confused. Okay, so if we go ahead and plug this into a calculator, we will end up with 9,906. And this is the balance after t years. So this is going to be in dollars, right? So our interpretation for f of 20 is after 20 years, the savings account will have $9,906. Alright, so we found and interpreted f of 20, and now we need to do the same thing for f prime of 20, which means we need to go ahead and calculate the derivative, right? We need to find f prime of t, which is the derivative with respect to t of our equation, 2000e to the 0.08 t. Alright, so we'll go ahead and use our constant multiple rule to pull out the 2,000. So then we just have the derivative of 0.08 times t. Okay, so this is one of our cases where we have e to the kx, or in this case, kt. Okay, so we take the derivative by bringing our k value, our constant, down, so we have 0.08, and then we leave everything else the same again, times e to the 0.08 t. Okay, and if we go ahead and multiply in the 2,000 times the 0.08, we'll end up with 160 e to the 0.08 t. Alright, so we went ahead and found the derivative, but now we need to evaluate it at 20. We need f prime of 20. Well, that's going to be 160 times e raised to the 0.08 times 20. And a calculator will tell us that this is 792. I'm not going to round the decimals. Alright, I'm not going to put that there either. So 792. So we're supposed to interpret this. And we remember that the derivative is a rate of change. So the first thing we notice is that we ended up with a positive value. So a positive value means that something is increasing. The fact that the savings account is gaining interest backs this up, that this is a correct number. Okay, so it should be positive, and it is, so that checks out. So our savings account must be increasing at this rate. So our interpretation is the savings account is growing by this $792 per year. Alright, because t was measured in years. So now we have found and interpreted both of the things that we were required to for this problem. Alright, so this is our last example for today, example 4, where we have the population of Nevada t years since 2000 is given by p is equal to 2.02 times 1.036 raised to the t, where p is in millions of people. The question is, at what rate was the population growing at the beginning of 2009? All right. So the first thing we notice about this problem, or the first thing maybe we should notice, is in the question it says at what rate. So we see the word rate, we should automatically start thinking derivative. Because the derivative is the rate of change, the instantaneous rate of change, matter of fact. All right? So maybe if we're not really sure what to do with this problem, we know that taking a derivative is probably a step in the right direction. Okay? So let's go ahead and do that. So we have p is equal to 2.02 times 1.036 to the t. So this is a function of t. All right, so really it's p of t. So we can go ahead and take the derivative with respect to t. So p prime of t is the derivative with respect to t of 2.02 times 1.036 to the t. All right. So the first thing we can do is use our constant multiple rule and pull out our 2.02. So then we just have that times the derivative, not with respect to x, with respect to t, I apologize, times the derivative of 1.036, that's a 6, to the t. All right, and this uses one of our exponential rules where we have the derivative of a to the power x or t or some other letter, that whatever the equation is using at the moment. All right, so we're going to have our 2.02 times the natural log of the a value, the base value, which is our 1.036. So we have natural log of 1.036 times everything by itself again. So the 1.036 to the t. All right, so this uses our exponential rules. All right. So if we go ahead and throw this into a calculator, just to clean this up a little bit, we'll end up with 0.07. So our 2.02 times this natural log is going to give us 0.07 times our 1.036 to the t. So this is our derivative here. All right, so the question asked us at what rate was the population growing at the beginning of 2009? So we need to find out, what are we supposed to calculate? Okay, we have the derivative here, and the derivative is the rate of change. So we need to find out when we're supposed to be calculating the derivative. So the population of Nevada, t years since 2000. Okay, at what rate was the population growing at the beginning of 2009? So if t is the number of years past 2000, then t should be equal to 9. Okay, so if we calculate this rate of change at t is equal to 9, that should give us how fast is it growing during the year 2009. All right, so we need to evaluate at t is equal to 9. So we have the derivative p prime of 9, which is 0.07 times 1.036 to the 9th power. All right. And again, a calculator will tell us that we end up with 0.096. And we remember that P was in millions of people. Okay, so this seems like a small number, this 0.096, but it's 0.096 million. All right, so the population, again, it's positive, so it's growing. So the population was growing at a rate of 0.096 million people per year at the start of the year 2009. All right, and that wraps up our final example for today. Please don't forget to take the comprehension quiz, and I'll see you in the next lecture.